Okay, continuing with, I guess we're up to 6A. Okay, so if you're creating a wave in a rope, how could you increase the speed? Okay, so speed is wavelength times frequency. These two have an inverse relationship. So, like if one goes up, the other goes down. Okay, um, and so really the only way we can increase the speed of the wave is to change the material, um, or the medium that the wave is in. So, say we were shaking it in water, for instance. If we wanted to increase the speed of the wave, then we would change it to something else. So it's like a mechanical wave that um, would move differently in a different medium, I guess. If we change the material that it's in, we can change its speed. A person is lying with their ear on the ground, another one's standing up. Their friend drops a heavy object. Who will hear the sound of the heavy object hitting the floor first and why? We actually went over this one in class. So this person is going to hear it through a solid, through the floor. This person is going to hear it through the air. So the person with their ear to the ground will hear it first because sound waves travel faster through solids. So they're going to hear it first before they do, because a denser material helps sound waves travel faster. So, describe the frequency and wavelength of a low pitch sound. So that'd be like a low sound. And pitch is connected to frequency. So that's going to have a lower frequency sound. And because these are inverse, you're going to have a longer wavelength there. And then for a high pitched sound, it'll be the opposite. You're going to have a higher frequency and a shorter or smaller wavelength. Because again, those two are inverse. Okay. What's the Doppler effect? So the Doppler effect is where a person is hearing a moving sound and they perceive a different frequency than the actual frequency that's coming from the sound. And that's because of the sound waves compressing or spreading out as the sound comes towards them or away from them. So here's a little table that helps explain that better. So let's say we've got a person that's standing on like the sidewalk and a car is going by them and it's honking its horn. So here the car is going to go by them. And here's a little table on the volume or loudness and then the pitch that they're going to hear as it goes by. So the person, as they're standing there, they hear this car coming towards them. They're going to be hearing a louder sound as it gets closer. And they're going to hear a higher pitch because the sound waves are compressed. They're more scrunched together as the sound is coming towards them. As it's passing directly in front of them, they're going to hear, that's where the sound's going to be the loudest because it'll be right in front of them. They're going to hear the actual frequency of the sound at that point because it'll be directly in front of them. Then as the sound moves away, the sound waves are going to spread out. So they're going to hear a lower volume because it's moving away from them. Also a lower pitch. Okay, so pitch is because of the sound waves either scrunching together as it comes towards you, you hear a higher pitch, or spreading out as it goes away from you and you hear a lower pitch. The person inside the car is going to hear the same loudness, the same pitch as the sound. They're going to hear the actual qualities of the sound because they're in the car. Their sound waves are not scrunching or spreading out. They're just the same because they're in the car. Okay. So here we've got a graphic of a wave. And that asks what type of wave this is. We can see that this is a transverse wave because it's got a perpendicular motion to the energy transfer. What is the amplitude? So let's see. Oh, I put that in the wrong place. Amplitude we're going to get from this value right here, our max displacement to our equilibrium line, and that's 1.5 meters. And I'm just reading that from the graph here. Wavelength we can get, let's see, we can get it a few ways. We could go from the beginning of a pattern to the end. So if I go from here to here, that looks like 4 meters to me. I could also look at a peak to a peak. So if I go from like 1 to 5, again, that's 4. Or I could go from a valley to a valley. 3 to 7, again, is 4. If the frequency is 80 hertz, what is the speed of the wave? So we're going to use wavelength times frequency as our equation. 4 meters times 80 hertz gives me 320 meters per second, just multiplying there. If you shook the wave with an increased frequency, what effect would that have on the wave speed? So if I increase the frequency, I'm just going to decrease the wavelength because wavelength and frequency are inverse. So that would not change the speed. We said earlier we'd have to put it in a different medium or a different material to change the speed. Okay. If I change one of these, the other one is going to go up or down correspondingly. So, all right, how fast does a sound wave travel if it's 18 degrees outside? So this is where we use this equation. So 331 plus 0.6 times our temperature value gives us our speed of our sound wave. I don't have my calculator handy. Let's see. I'll just use my phone. So 0.6 times 18 is 10.8, and then I'm going to add that to 331. That gives me 341.8. And that's in meters per second. Okay. A dolphin using sonar sends out a 500 hertz wave with a 3 meter wavelength. Okay, so what is the period of this wave? Remember, period is 1 over frequency. So 500 hertz is the frequency. 1 over 500 is going to give me 0.002 seconds. So that's my number of seconds per cycle of that wave. What's the speed of the wave? So I'm going to use wavelength times frequency. We said that's got a wavelength of 3 meters and a frequency of 500 hertz. So that's going to give me 1,500 meters per second. So I'm just multiplying frequency by wavelength there. If the wave's frequency doubled to 1,000 hertz, describe what would happen to the speed of the wave, calculate the new wavelength. So now we've got a different wave here. Well, the speed is going to be the same again. If we're in the same material, the same medium, then my speed is going to stay the same. So if my frequency now doubles to 1,000, my speed is going to stay 1,500. Now my frequency is 1,000, and I'm going to solve for my new wavelength here. I'm going to do 1,500 divided by 1,000. Gives me 1.5 meters. So again, wavelength and frequency are inverse, and if you're in the same medium, same temperature, all that kind of stuff, your speed is going to stay the same. So I'm using the same 1,500, but now I'm saying my frequency doubled to 1,000. that means my wavelength, my frequency goes up, my wavelength is going to go down. See, my original wavelength was 3 meters. Now it's dropped. Okay, so if my frequency doubled, my wavelength drops in half. Because those two have an inverse relationship. Okay. All right. One more video after this.